All right, welcome. So today we're going to be working with this red wine quality dataset from Kaggle. At a very high level, it has 1,600 data points of different wines, and each wine has 11 features correlated to it, and those features are physical attributes about the wine. And each wine also has an associated label, which is a quality score given by an expert, and this score is between 0 and 10. So we are going to follow the CRISP DM framework of model development. Before we delve into this dataset, we first need to give a reason why we would want to build this predictive model in the first place. Imagine that there's a company in the wine industry, and it owns a vineyard with the ability to control various attributes about the wine, the very same ones that we saw in the dataset. Naturally, this vineyard wants to produce the best wine possible, and the ability to predict the score it will receive from the experts before it ships the wine to the consumers is incredibly valuable. Just as an example, say the model predicts the wine won't score as well as hoped. The vineyard may be able to physically alter the wine so that it has more favorable attributes to score higher before it sells the wine and eventually gets scored by the experts. So we have the data that we need, which includes almost 1,600 data points and their respective expert scores, also including the 11 features with which we can use to build our models. In fact, this data is almost too good as there are no missing features or data points. So for this example, I've gone ahead and removed every 10th volatile acidity feature so that we can deal with data imputation. So if we look below, you can see right here that the volatile acidity distribution is normal, so almost normal, so we can actually impute the mean of the data, and that's okay. So once we have this data in hand, we most likely need to do some manipulation before it's actually usable. So for one thing, if the scales are wildly different, so just comparing right here, this is a great example, total sulfur dioxide. This actually ranges from 6 to 289, and when you compare that to something like density, which ranges between 0.99 and 1, it is obvious that we need to normalize these features as these scales are just wildly different. If we look farther down in this code, we can see that right here is where I removed every 10th volatile acidity feature in the dataset and then imputed it. And in this block right here, this is where we normalized all the features in the dataset. Finally, if we come down here, we can check the collinearity between the variables to see if any are immediately removable. And just at first glance, they all look like they're pretty independent of each other, which to me is personally a little bit surprising. And also, if we look at the distributions of all of these normalized features, they all mostly look normal. So I actually don't think that we'll need to do any extreme transformations on these features. So now we're ready to start building models. We're going to create a linear regression model, a decision tree, and a neural network to try and predict the expert scores of a given wine. This data is really interesting as the resulting 0 to 10 quality score can be seen kind of as both a continuous variable as well as a classification between 10 different classes. So to try out the continuous variable approach, I think a neural network and a linear regression model make a lot of sense. And to try out the decision tree classification definitely makes more sense in that case. So I've gone ahead and split out the manipulated data set into a train set and a test set with a 4/5 to 1/5 split respectively. Here I've created a linear regression model using the standard LM function, using some of the features in the dataset, not all of them. I've already actually gone through and performed stepwise backwards elimination of the least significant variable until all of these features still present in the model are significant and they have a p-value of less than 0.05. If we go ahead and predict the quality score on our test set, we can see that we've achieved a prediction accuracy of 0.49, a little bit above 0.49. And if we go ahead and perform tenfold, k-fold cross-validation on the entire data set, this results in an accuracy of almost 0.48. Here I've created the second model, the decision tree. I used the rpart function from the rpart library, and I specifically used the classification method when building this decision tree. So similarly to before, if we predict this against our test set, we obtain an accuracy of 0.59, a little bit above that, and using the tenfold cross-validation over the entire data set, we obtain an average accuracy of 0.57. So finally, I've created this neural network from the neural net library, and as before, I've decided to only use the features that were deemed most significant from the linear regression model. And this model did pretty well. It achieved an average accuracy of 0.53 for both the test set as well as tenfold k cross-validation, but we can do better than that. So to improve this model, I've added some hidden layers and found 2 to be the best without going overboard. And this model actually did pretty well. It achieved an accuracy of 0.55 on both the test set and the cross-validation. So adding those hidden layers was an improvement over no hidden layers. This brings us to evaluation. When evaluating these models, we need to keep a couple things in mind. There are 11 possible scores to give 0 through 10, so naively, a predictive model that chose randomly would have an accuracy of 0.09 at the very best. The quality labels, however, are very far from uniformly distributed and are biased towards the middle as might be expected. The mode of the quality scores in the dataset is 5, so if we had a, quote, select 5 model that predicted a score of 5 every single time, this model would have a much higher accuracy at 0.45. So this should be the benchmark that we are testing against. So looking at the table below, every single model did better than our, quote, select 5 model, so they're all at least better than that. Giving a bit more weight to the k-fold accuracies, the decision tree performed the best with an accuracy of 0.57, but the neural network came a close second at 0.55. The linear regression model did the worst and was only slightly better than the select 5 model. So taking the decision tree in the neural network, there are a couple of reasons why the decision tree is better overall for this situation. Yes, it has better accuracy, but it also provides the vineyard with tangible reasons why a wine might score higher if some feature is different. The black box neural network cannot provide that, so between these three, the decision tree is definitely the most useful. Lastly, if we were to deploy this within the company, we could create some simple software interface where an employee at the vineyard could enter in data about a wine they are creating and obtain a predicted expert score. The employee could then test altering physical attributes of the wine within the interface itself to see if they can improve the predicted score of the wine, and then actually go and make those physical adjustments to the wine as it's being produced before it gets shipped off to the consumer. So we've completed the CRISP-DM framework, and now the cycle would continue back to the beginning as improvements can be made. To summarize, we've established a business proposition, obtained and transformed data, created 3 different models, evaluated the performance of those models, and then discussed a possible deployment to complete the business proposition goal. Some interesting things to note about the nature of this data. Within the data preparation and modeling phases, we could have created models with a different goal that would have changed the ways that we used the data and evaluated the models. For example, we could have decided to create models that predicted whether a wine was simply good or bad. A quality score of 6 or higher is good, and a quality score equal or below 6 is bad. And with that, we could have created binary classification models. This would have led to much different results and most likely higher accuracies, but it really just depends on what is desired by the vineyard. In this case, we decided that we wanted models to predict the score itself, and that's okay. The point is that there are multiple options to do this, which is really a fun and exciting uh, aspect from a data scientist point of view. Anyway, that is all. Thank you for watching.